Okay, so we were looking at computation across the engineering curriculum, and so we're going to talk about the issues that we feel arise when one thinks about computation, both in early courses that come when students are first introduced to programming, and then later on when students are asked to use programming in the context of engineering. And we're kind of doing this as a tag team, so I'll hand it off to Jennifer.
We identify 3 goals, or say 3 hopes. And those 3 hopes, the first one is better understanding domain-specific materials through computation. And this goal coming from, traditional engineers, we were creating, and we were fixing things. And now engineering, we were making, and we also creating, but we based on computational results. Computer tell us how to fix, how to make, how to create better things. So this is today's engineer is not only about creating, it's about computing too. So the second goal, it is better understanding of the strengths and faults of advanced computational tools. We have a lot of computational tools in our practice, in our classroom, in our every disciplinary teachings. There is array of softwares, array of computer models you can use. So how to have our students, gradually be able to understand those software, be able to use them correctly in their practice. So this is the second goal. The third goal we have, it is, we're trying to educating our engineer students. The tradition, it is creating, make. Now we want them computing too. So the future engineer doesn't only know how to create, but also knows how to computing, how to infuse this computational thinking into their daily engineering creating inventions. This is our one goal too.
So we've all been trying to do this in our classes, and we've encountered a number of challenges, so I'll sort of talk about them. One thing we've noticed is that in almost all the universities we come from, people learn their computing in computer science initially, but then they try to deploy it in our individual fields, and there's sometimes a disconnect there. So we're just trying to think about how do we kind of bridge that disconnect. We also find that often they just don't have enough programming skills for what we're trying to do, and so this is depending on the field and so forth, but it's often an issue. So several of us have actually tried this in various ways. So on the right there's an example from my class where we build circuits on circuit boards, test them, and then actually also simulate them in MATLAB and try to compare the results. And what we find from that is that some students really like this. The people with a sort of computational mindset to begin with come back and they understand circuits now better because they thought about them in an algorithmic way rather than just as a physics way. And other students just see it as just a pain. So the question kind of is how do we ensure that the mechanics of actually doing the programming doesn't distract from their actual learning the concepts we want them to learn? How do we make that actually a strength, not a weakness? So one piece of this is how do we then integrate these tools into our traditional courses and kind of create an advocacy within our faculty for this approach to doing things rather than this traditional hand analysis approach that we're all used to. And what we found is a big problem with this is when we try to deploy these things, often our senior faculty push back, and when you push them long enough, it turns out they just don't know MATLAB. And so the problem is they don't want to use MATLAB in their course because, not because they're against computation, but because they know they can't use Fortran with their students, and MATLAB is not an option. So that's just kind of what we're saying. I should say we had one more challenge that we did not face up to, which is we wanted to have a gimmick too. We thought we'd format it all in MATLAB script. But apparently that's really ugly, I'm told. So we decided not to.
Thanks. And you can see, computation is a very pervasive thing across engineering, so many diverse challenges. And we have a few success stories. I'm going to focus on a few, the more interesting ones, 4 of them. The first one, you can see it on the side, the screencast, when you embed code in an HTML that students can run real time. So you combine the theory behind the code with the code itself, but not just an abstract code, something where the student can go they can change parameters and they can visualize immediately what the results. And that's a very powerful as a learning tool. Some other things, this is one of the cases where flipping works amazingly well. So we focus on online instructional computation, and then when you go in class, you spend a lot of time analyzing, verifying, validating code. And this works very good in the 101 classes, but it works very well when you look at the more advanced classes, where you do have that challenge that you have students that don't have the necessary background. And then you can play with these online tools, having different tracks. The students that understand, they go a little bit faster. For the students that do don't have the background, they can go in a different track where they spend more time of trying to fill in the gaps. And the last two are a little bit tied together, so you don't present abstract computing. You try to tie it to exercises in analysis and labs. So I can solve this problem like a closed-form solution analytically, and then I can use computational tools to get to the answer in a little bit different way. This gives you a multiple viewpoints of how do you approach one problem. So you understand what the power of computation as a computation is, but also you figure out, yeah, there are ways to validate those computational tools. I shouldn't just take their answer as the golden rule. There are other ways that I can solve the problem, and maybe in a simplistic a little bit version to see if my answers make sense.
Okay, so assessing impact. So this is one of the things that I've been particularly interested in coming here, and also within the group discussing these different ways. And this, of course, impacts computations. How do we integrate this into our classes, and how do we determine is it useful? Because there's all these different sorts of ways to do this. And not only in just computations, but we've had a lot of discussions on the difference in just classically using a textbook, or I post my notes online. Is that a good thing or bad thing? Are students going to actually write down things? And also the online content. So I've been interested in tracking these things. I'll ask students, what do they use before class? Give me a level of understanding on, say, a scale 1 to 10. They come to class, we discuss it, they give me this score again, and then they take a quiz. So we try to figure out, do they really know what they think they know? And we do things like uncertainty quantification on those numbers, using things like Bayesian or evidence theory techniques. So that comes into these exit surveys, pre and post test, to not only give feedback, like was discussed before, feedback to the faculty, but also feedback to them, so we can show them, yes, maybe if you look at the online content for this particular topic, it does give you accelerated learning. And that comes into these correlated self-assessments that we've done or discussed. The next point is the first and second year tracking these things and figuring out the best way to introduce computational tools in the first 1 or 2 years as freshmen or sophomore, and then find out as they're juniors or seniors, are they then applying these in more advanced ways and learning that way. And then, of course, alumni surveys discussing or getting feedback in postgraduate. Are they using commercial software now? Are they developing their own code? What did they take out of this curricula?
So some of this material, by its very nature, we find is possibly easier to scale up. For example, I've been putting many of my lectures online. University of Virginia has something called the Produce program, where you can simultaneously teach to many colleges across Virginia. But what I found is very interesting is by putting my lectures online and actually putting exercises online, I was getting students from industry, who had a 2-year undergrad curriculum. They did not know the material, they knew the results. And so they kept taking this class and coming back to me and said, well, I never knew where this came from. And I didn't have a way of taking this class because I have a day job, but I could pace myself up, kind of learn this thing hands-on through the simulations. And so I got a lot of enthusiastic feedback. And I'm now trying to explore ways of going beyond Virginia. There's an example, which is the NanoHub, which I was involved with when I was at Purdue. The NanoHub started as an online portal for various nano-related simulation tools. And then they started expanding to courses. And now they have this interesting idea that I'm kind of plugged into called the NanoHub University, which is this decentralized kind of university across many colleges where you have professors like me or other places who go in, suggest courses, and actually teach courses. So it's not just reaching a broad student body, but it's also reaching a broad faculty group across the country and tapping into their expertise. The other thing we do is simulation tools that are actually put online. And one of the things I've also found is with some creativity, you can make this transdisciplinary. So for example, in my class, I teach reasonably advanced topics, but I try to take each of them, whittle them down to their essences that I can convert into a small MATLAB code. So I get students from computer science, chemistry, material science, taking the class. And again, traditionally, this would have taken many years of physics courses. But in the physics courses, what you do typically is you'd learn many, many weeks of how to solve a Schrodinger equation. And so what I do is I say, okay, now don't focus on how you solve it. Just use a MATLAB code that does it for you. Focus on the how and or the what. What does the answer look like, and not how it's being solved. And that way I find I can go through many, many weeks of material in a very short time. So there's a lot of opportunity for scaling up materials, collaboration, codes, and so on. But of course, it has to be done with some caution. Not every material can immediately be scaled up. There may be certain things that are participatory and requires hands-on laboratory. So just like anything else, it has to be done with some caution. But we see a lot of opportunities for scaling much of our simulation tools online.
Okay, so I thought there was one thing missing from the questions we were asked to respond to, so I was pushing the group to ask, because I think when engineers think about education, and this is something my education collaborator has sort of pushed me to think more about, we tend to think about what are the education goals and what are the implementation hurdles, but we tend not to think about what are the underlying education questions. And my favorite question on here is, why aren't there dinosaur ghosts? But in the context of this topic, we wanted to identify what the education questions were, and we think there are a bunch of questions about, when does computation actually assist in learning engineering? How does it assist in learning engineering? And how does contextualizing computation assist in motivating students to learn computation and in their learning of computation? And when does it hinder? And how does it hinder those kinds of learning? So I think there are some sort of deep underlying questions there that could be of interest to education people as well as engineering people. Also, I had talked a little bit in my talk about cognitive overload. What are the techniques we could use to minimize cognitive overload? And one of the things that sort of comes up whenever you try to get students to deploy computation is that before they can make something into an algorithm, they have to understand it conceptually. They have to have a toy model in mind or somehow modelize the system. And so that interaction between modeling and computation, I think, is not trivial, and there could be some rich study there. In addition, there was some discussion about whether it's, under what circumstances is it useful to provide focused computational courses, and under what circumstances should these things be embedded so students see them in that broader context. So I think that's the end of our presentation, so we're happy to take questions.
I'm wondering, have you identified aspects of programs and disciplines that at a fundamental level govern whether you would want to teach more computation early in the curriculum versus late in the curriculum?
So my observation on this, I can answer, is I do circuits in electrical engineering, and our big problem there is that if we wait until late, they've been handed a full-bore simulator and they don't understand it and they'll never go back. So we kind of have to get them to them early enough that they're still sort of have a fresh mind on how these things work, so we can give them a little bit of a sense for that before we hand them the full-blown software package that they'll never actually understand. Because otherwise we find they use it blindly, they don't know what's wrong with it, and they're sort of addicted to that point, and they just never think. So I think in the context of people sort of dealing with complex systems, probably early enough so that they don't sort of fall into that trap, would be my feeling.
So suppose, I'll preface this, I teach CS1, okay? So I guess I'll just say that when do you introduce computing into your curriculum? Because I have faculty that come to me and say, I have students who don't know how to write a for loop. And if you think I let a student out of CS1 without writing a for loop, you don't know much about what we teach in computer science. And so I guess I'd ask my colleagues in other engineering disciplines, we're trying to meet you halfway by saying, okay, let's do some examples, let's do some large data set, let's do some simulation and modeling. why not in the computing courses in other disciplines, you meet us a little halfway and say, okay, you learned how to do this type of looping construct in Java, so now let's transition this. I mean, I think we can have an opportunity to pass the baton off to y'all without the individual disciplines doing your own computing course and us in CS say, oh, we're going to go do how computing is beautiful. We don't need to talk about engineering at all. I mean, there is a way we can work here. So how can you help us help you?
Yeah, I mean, I think it's sort of a dynamic, evolving situation. You know, like at Hopkins, the disciplines have started pulling computing back, and computer science has started to adjust. I think because they realize that it's going to be an issue for them if this trend continues. And so there's now been a Python course that's structured around engineering examples that's available for students. And so perhaps that will, you know, be sufficient for enough departments that they'll decide that that's the kind of computing they want their students to learn. And they came to me and I shared all my example problems with them, and I'm happy. The more contextualized computing goes on, the happier I am. You know, but I think it's similar to the problem we have with calculus. You know, we send a lot of students, I don't know how you guys feel at your campuses, but we send a lot of students to the math department to learn math, and yet they oftentimes come into our class, and when you ask them to apply the calculus, they look at you like, you know, they've never seen it before. And I think a lot of that is because we tend to do the same thing with math. They apply math out of context, and then they don't realize how and when to deploy it. So, I mean, I think it's good. There should be a conversation like this between the user disciplines and computer science. Yeah.
So, sorry. Yeah, I just wanted to comment that this is also something where we should be pushing the K-12 community to really have computing, at least at a very basic level, be introduced earlier. That, you know, in today's world, mathematics and computation are not so different that you have to wait till engineering college and often junior year before you see how to write a for loop in your life. I just, yeah, comment.
This is another hobby horse of mine, so I have to. So, you know, actually, I think it's been my perception, and I don't have data behind this, so somebody should check me, but I think when I was going to high school, more students had access to programming classes, and particularly to AP computer science, than they do now. And my understanding, I had asked around as to why that is, and this is not to beat up on computer science, I'm sorry, but my understanding was that computer science got more involved in designing the AP exam and professionalized the AP exam to become more about data structures and object-oriented programming and the things that computer scientists feel are essential, which I totally understand, but the result at the end of the day was that there were few high school teachers qualified to teach the AP exam. And so many fewer schools actually offer this exam now. And so I think, you know, there's some dynamic going on there that also probably needs some attention. But I don't know, maybe I should, yeah, I don't want to become too controversial. Yeah.